Electromagnetic radiation will act as a dual character, that is one wave-like and another one is particle-like properties. How much distance is travelled in 1 second is called velocity of the wave. There are different kinds of units are present in electromagnetic radiation, that is frequency is expressed in cycles per second or hertz. Hello everyone, welcome back to the session 3, that is structure of atom. I am Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. So last class what we have seen, that is about atomic models, Thomson model of atom, Rutherford model of atom and representation of element. So these contents we have seen in the last class. So now about developments leading to the Bohr's model of atom we are looking up, and wave nature of electromagnetic radiation and characteristics of electromagnetic radiation and particle nature of electromagnetic radiation. About two characters or dual nature of electromagnetic radiation we are looking up today. So we'll see first one, developments leading to the Bohr's model of atom. So what Niels Bohr is telling means, or Niels Bohr used the following developments to improve Rutherford atomic model. So Rutherford atomic model failed due to some circumstances about stability and the charged radiation due to the accelerated electrons. Those things we have seen in our last class. Today we are looking up about how Niels Bohr have outcome regarding about Rutherford atomic model. Okay, what he told or what he has done with this experiment means dual character of the electromagnetic radiation, which means that radiations possess both wave-like and particle-like properties. What does it mean? Electromagnetic radiation will act as a dual character, that is one wave-like and another one is particle-like properties. Next one, experimental results regarding atomic spectra which can be explained only by assuming quantized electronic energy levels in atoms. Here he explained about the atomic spectra and also explained by assuming a quantized energy levels. See, quantized means in a packed energy levels in an atom. So this we will see in our coming sessions. Today we are going to be explain about wave-like structure or acting as a wave-like electromagnetic radiation. So wave nature of electromagnetic radiation, how it has been came through means, first James Maxwell in 1870 was suggested that when electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the form of waves called electromagnetic waves or electromagnetic radiations. What he told, when electrically charged particle like electrons will be moving around the nucleus, it will be accelerated. Correct? When after acceleration, it will form or it will emit some radiations. Those radiations are known as electromagnetic waves or electromagnetic radiations. It will be transmitted in form of waves. So we will call it as electromagnetic waves. See, first what they have told means wave nature of electromagnetic radiation. The radiations which are associated with electrical and magnetic fields are called electromagnetic radiations. The radiation which are associated means it has been a relationship between an electrical field and a magnetic field, that radiations will call it as electromagnetic radiations. When electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. These things we have seen from James Maxwell experiment, that is when electrically charged particle is under acceleration, it will emit some radiations by alternating the electrical field and magnetic field. It will alternate both the fields and it will form or it will emit some radiation when it has been under the accelerated electrically charged particle. These fields are transmitted in the form of waves. It will emit or it will be transmitted. After emission of radiation, it should be transmitted, right? So that transmitted radiations will transmit in the form of waves. So see here, this is the electrical field and This is the magnetic field. These two fields, both the fields are perpendicular to each other. Means if this is the electrical field, this will be the magnetic field. The both fields will be perpendicular to one another, and also this is the propagation direction. How the accelerated or how the path of electrons will move here, like that, and both the magnetic field and electrical field will be perpendicular to each other. This direction of propagation or propagation direction will perpendicular to both of the fields. Next, we will see characteristics of electromagnetic radiation. What are the characteristics of electromagnetic radiations? Means there is wavelength, frequency, velocity and wave number. So, we will see one by one here. First, we will see the wavelength. It is the distance between two neighboring crest or trough. Crest or trough means, see, this is the overall wave picture and it has been named here. This is trough. The lower region of the wave is known as trough. The upper region of wave is known as crest and the lower region of wave is known as trough. What we are looking up, what is wavelength? It is the distance between two neighboring crest or two neighboring trough. If it is a crest and this is a crest, see here, this is wavelength. Okay, the distance between the neighboring crest to crest or trough. If it is here another trough is there, this is also a wavelength. Next, it will be denoted as lambda. This symbol will call it as lambda. And next, frequency, it may be defined as the number of waves which pass through a particular point in 1 second. If there is a one point here, how many waves will reach in 1 second or how many waves will pass in 1 second, this we will call it as a frequency. In 1 second, how many number of waves will pass through that particular point. So, it will be designated as nu. It will be looked as V only but little bit tilted. So, it will call it as nu. Next, velocity, the distance travelled by a wave in 1 second is called velocity of the wave. How much distance is travelled in 1 second is called velocity of the wave. Okay. Here you can see the distance. This is the distance point. Overall, what is the direction here? That is distance. The number of waves, how much distance will pass. Okay. Next, in vacuum, all the types of electromagnetic radiations travel with the same velocity. Okay. In vacuum, all the types of electromagnetic radiation will pass in the same velocity. It will be equal to the velocity of light, that is 3 into 10 to the power of 8 meter per second. So, velocity of light is 3 into 10 to the power of 8 meter per second. So, all the electromagnetic radiation which are having the same velocity in vacuum, it will be equal to the velocity of light, that is 3 into 10 to the power of 8, and it will be denoted by C or small v. It can be denoted as V also or it can be denoted as C also. Okay. Next, wave number. It may be defined as the number of wavelengths per unit length. For the unit length, how many wavelengths will be reached, that will be known as wave number. It is nu bar. For the nu, one bar line will be given, for that we will call it as nu bar. Okay. We will see here some of the characteristics of another characteristics of electromagnetic radiation. So, if it is a wavelength is long, that time frequency will be low. Means it both are inversely proportional to each other. Okay. If it is wavelength region is long, that time frequency will be low. If it is wavelength will be short, that time frequency will be high. Another characteristics of or the property of the electromagnetic radiation or electromagnetic wave, and also the wave number is inversely proportional to the wavelength. Okay. This is another one. The wave number is inversely proportional to the wavelength. This is the overall characteristics of electromagnetic radiation. Next, properties of electromagnetic radiation. Now, what last slide or what last topic we have seen overall the characteristics about the simple or basic things of electromagnetic wave we have seen, and here we are looking up about properties of electromagnetic radiation. How the electromagnetic radiation will be oscillating. The oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other and both are perpendicular to the direction of propagation of the wave. Okay, I have already told that the oscillating electric and magnetic field, both the fields of electric and magnetic field are perpendicular to each other. Okay, and direction of propagation of wave is perpendicular to both of the electric and magnetic field. Okay, the electromagnetic waves do not require medium and can move in vacuum. So electromagnetic radiation doesn't need any medium and it will travel in vacuum. We have seen in last slide, that is in vacuum all the electromagnetic radiation will be having the same velocity. Electromagnetic radiations will differ from one another in wavelength or frequency. These constitute electromagnetic spectrum. Electromagnetic radiation having different wavelength and different frequency. One electromagnetic radiation is differ from another. Okay. So overall all the different kinds of wavelengths, all the different kinds of frequencies having radiations will constitute electromagnetic spectrum. Okay, different kinds of units are used to represent the electromagnetic radiation. There are different kinds of units are present in electromagnetic radiation, that is frequency is expressed in cycles per second or hertz, and wavelength, that is lambda, is expressed in angstrom or nanometer. Angstrom will be 10 to the power of minus 10 and nanometer is 10 to the power of 9. So this is the overall different kinds of units used in the electromagnetic radiation. Next, in vacuum all the types of electromagnetic radiation regardless of wavelength or travel at the same speed. In vacuum, regarding about wavelength, all will travel in the same speed, that is 3 into 10 to the power of 8 meter per second. Okay, these are the characteristics of or properties of electromagnetic radiation. This is electromagnetic spectrum. The arrangement of different types of electromagnetic radiations in the order of increasing wavelength or decreasing frequencies is known as electromagnetic spectrum. Okay, see here it will be in an increasing wavelength or it will be in increasing wavelength or in a decreasing frequency. They have seen from the right to left side, that's why they are showing here in increasing frequency. We have to consider from left to right, that time it will show as a decreasing frequency. At that time increasing wavelength we can see here. And what are the rays or what are the electromagnetic radiations you can see here means, this is gamma rays, this is X-rays, this is UV rays, and in between visible region is there. It contains WIBGYOR region from 400 nanometer to 700 nanometer. You know the WIBGYOR region, that is violet, indigo, blue, green, yellow, orange, red. This is the visible spectrum here. And infrared, that is IR region, and microwave region, completely radio waves region here. Okay. So overall electromagnetic spectrum is here and it is designated as a increasing wavelength having and decreasing frequency, and different kinds of electromagnetic radiations will be present here. Okay. See here frequency is designated in hertz and wavelength is designated in lambda, that is in meters. Next, relationship between the velocity, frequency and wavelength. What we have seen in electromagnetic spectrum, that is velocity, frequency and wavelength, how it has been related one to each other means, we can see here velocity equals frequency into wavelength. How velocity is designated, that is c, and this is frequency is nu and lambda. And also if you want to find out only frequency, that time we can use this relation nu equals c by lambda, means frequency equals velocity by lambda. Here one problem is given, how we can solve this one. Problems, that is the Vividh Bharati station of All India Radio at Delhi broadcast on a frequency of 1368 kilohertz kHz means kilohertz. Calculate the wavelength of the electromagnetic radiation emitted by the transmitter. Which part of the electromagnetic spectrum does it belong to? Here we have to calculate the wavelength, and they have given the frequency in terms of kilohertz. So, and they have asked also, after finding the wavelength in the electromagnetic spectrum, for which part or which region it will belongs to. So, we will find out. We know that lambda equals c by nu, means wavelength equals velocity by nu. Okay, we have to find out lambda, no. So, we have to interchanging this equation, that's all. So, what is velocity? We know that 3 into 10 to the power of 8, and they have given the frequency here. Why we have given the 10 to the power of 3 means kilohertz. Kilo means 10 to the power of 3, that's why 10 to the power of 3 here. So, how it has become 10 to the power of 5 means, we are taking this 10 to the power of 3 to the nominator side. When we have taken the nominator side, it will become 10 to the power of minus 3. Due to multiplication, we have to add up. Due to minus 3 is here, we will get 8 minus 3, 10 to the power of 5. Same thing we will be having. After 3 into 10 to the power of 5 by 1368, we will get 0.0021929 into 10 to the power of 5. After, we can rounding up this one. See here 5, 1, 2, 3, 4, 5. That's why we will get 219.3 meter. Since we are calculating the wavelength, we have to write its unit, that is meter. So, after getting overall this one, this wavelength region belongs to radio wave. You can cross check by seeing the electromagnetic spectrum what we have shown in the previous slides. You will get this region in that spectrum, and it will belongs to radio wave region. Okay. We will see another problem here. Here we have to find out wave number, that is calculate wave number and frequency of yellow radiation having wavelength, that is 5800 angstrom. Okay. Again we have to find out here wavelength and also frequency. Wave number and frequency, wavelength they have given here 5800 angstrom, that we have to be converted. Angstrom means 10 to the power of minus 10 meter. First we are finding up wave number. I have told already wave number is equal to reciprocal of wavelength. That only they have written here the equation. 1 by, they have given the wavelength. So, we have written here, and we will get 1.724 into 10 to the power of 6. We are converting it to meter into centimeter. So, we have converted here. We will get 1.724 into 10 to the power of 4 centimeter. Next, we have to find out frequency. For frequency, we have already used this equation, nu equals c by lambda, that is velocity 3 into 10 to the power of 8 by lambda means wavelength. We have converted here, we have to take up here, and see here we are converting this and we are writing here 2 zeros, and we are converting it to here right side. These significant notations you will see in your unit 1, that is how they will convert scientific notation. By that factor 58 into 10 to the power of 2 into 10 to the power of minus 10. After these two getting difference, you will get 10 to the power of minus 8. Overall, calculating these terms, you will get 0.0517 into 10 to the power of 16. After rounding up, we are converting into 5.17 into 10 to the power of 14, means 2 here. See, we are getting 1 and 2. So, we have to minus 2 points, 2 decimals, that is 10 to the power of 14. Why hertz? Frequency will be given in terms of hertz. So, we have to write the units for every problem at the end of the solution. Without the units, you will not get full marks for the numerical problems. That's why we have to write units at the end of the solution. Here also we have written. Okay. Next, we'll see the drawbacks of Maxwell theory. After so many things, he got some drawbacks. What they are drawbacks means the nature of radiation which are emitted by hot bodies, means the whatever the emissions we will get, or the object will get some radiations, he could not find out the nature. So that is one drawback. The ejection of electrons from the surface of certain metals when light radiations strike the surface, this is known as photoelectric effect. He could not explain why certain metals will emit some radiations when the electrons will strike up the surface. That is known as photoelectric effect. He could not explain that effect. That is one drawback. Another one, the spectral lines are emitted by certain elements. So many by certain elements, it will emit some line spectrums. That will also we'll see in next session. These are known as line spectrum. In order to explain the Max Planck put forward a theory known as Planck's quantum theory. He could not explain how the elements will be emitting some lines, that is known as line spectrum. So Max Planck have been explained that theory, but Maxwell could not explain. Okay, these are the drawbacks of Maxwell theory. Next, till the previous slides we have seen the wave nature of the electromagnetic wave. Now we are looking up how the particle nature of electromagnetic radiation will look forward. Okay, first we will see the black body radiation and explained by Planck's quantum theory. We know that after the drawback of Maxwell, Max Planck have come to explain the so many theories, that is black body radiation and photoelectric effect, by using particle nature of electromagnetic radiation. Now we are looking up black body radiation. What is that black body radiations means? An ideal black body is perfect absorber or a perfect emitter of radiation. Whatever the black body content is there, it is a good absorber of radiation or a good emitter of radiation. It emits or absorbs radiation of all frequencies when fall on its surface. Means on a surface of black body, all the frequencies can absorb or it can emit all the frequencies. Okay. A black body absorbs all the radiation that are incident or falling on it. When such a body is heated, it emits energy in the form of radiation. When the black body is heated up, that time only it will emit with all kinds of radiation in the form of radiation, and it will emit as energy. It will emit energy in the form of radiation when a black body absorbs the light or absorbs the heat. It will get heated and it will emit energy in the form of radiation. When a black body such as an iron rod is heated in a furnace, it undergoes series of changes in color. Means we are giving a example here. When iron rod is heated in a furnace, it will go series of changes. In what? With respect to it will change? It will changes in color. So the red color changes to yellow. First step, it will red color change to yellow and then changes to white. Finally it becomes to blue at very high temperature. So we know that rod will be in a blackish color. Though after first heating, it will change to red color to yellow color, finally white, and complete end at a very high temperature, it will turn up to blue color. This is the example for black body radiation. So next, particle nature of electromagnetic radiation by Planck's quantum theory. How it has been explained, we'll see. The radiant energy emitted or absorbed discontinuously in the form of small energy packets called quanta or photons. What he is telling, the radiant energy emitted, whatever the radiations emitted or absorbed, it will be in a discontinuous way. Okay, means it will be having in a continuous, again it will be like this. Some discontinuity will be having as a packet. Small energy of packets will be present. Okay, that we will call it as quanta. In case of light, these energy packets are known as photons. It will be called as quantum, quanta or photons. With respect to light, we will call as photons. The energy of each quantum is directly proportional to frequency of radiation. What they are telling, energy of the quantum is directly proportional to the frequency. That is only we have written in the equation. E is directly proportional to nu, this is frequency, and here we have given a constant. H is Planck's constant. So whenever we are having a directional proportionality, so then that time we will introduce, or whatever the chemist will introduce a constant. Here they have introduced H, that is Planck's constant, and nu is frequency. We know that. E is energy. Okay, H is Planck's constant. The H value is 6.626 into 10 to the power of minus 34 joules. This is the second postulate. The total amount of energy emitted or absorbed by a body is in integral multiple of quantum, that is E equals H n H nu. Means whatever the total amount of energy emitted, it will be in a complete integral multiple of quantum. Means whatever the n here, it will be in complete form, or 1, 2, 3, 4. Not will be in as a quarter or half or 3 by 4 like that. It will be in a complete integer. So that's why n is an integer, that is 1, 2, 3, 4 or completely so on. Means it will be in a complete form, not as a fractionate form. Okay. So next, again we are looking up or revising the radiant energy emitted or absorbed discontinuously in the form of small packets, that is quanta or photons we will call. This is the first postulate of Planck's quantum theory. Next Planck's quantum theory, that is second postulate, is the energy of the quantum is directly proportional to the frequency of radiation, that is energy is directly proportional to frequency. Here one constant has been introduced, that constant we'll call it as Planck's constant. The Planck's constant value is 6.626 into 10 to the power of minus 34 joules. This is the second postulate. Next, the total amount of energy emitted or absorbed by a body is integral multiple of quantum. So E equals n H nu. N is an integer, that is will be in a complete number or a whole number, that is 1, 2, 3, 4. Okay. In a next class, we'll see about photoelectric effect and some of the problems. Okay. So thank you. We'll see in the next session.